You are standing at the end of a diving board as shown in the figure below. A, what is the force from the quote center support, which is not exactly in the center, and B, what is the force from the leftmost support. We recognize this is an equilibrium problem, since there is no acceleration in the x direction, nor in the y, nor is there an angular acceleration. This means that as a force problem, we will draw a free body diagram. However, we will sum the forces in each relevant direction so that they're equal to 0. We begin an equilibrium problem by identifying that object that has the greatest number of forces acting on it and draw the free body diagram there. In this problem, that would clearly be the diving board. And since we'll be dealing with torques, we will draw the diving board's free body diagram as an extended object free body diagram, with this line representing the diving board. The first force we think of in any free body diagram is that of gravity, and gravity does indeed act on the diving board. The gravity force is located at the center of mass, which is in the center of the diving board itself, and is directed downward of an amount m times g. Next, we see that there is a person standing on the diving board. The person would experience a normal force underneath their feet, and that would be the force of the diving board upon the person. The force of the person on the diving board is equal and opposite to that, so it is 80 times g downward and located at the very end of the diving board itself. There's a subtlety when labeling the directions of the forces due to the two support points, and let's deal with that now. The subtlety has to do with the fact that the two supports are both to one side of the center of mass of the object. If we imagine attempting to hold something up with two fingers, we can imagine putting one finger underneath the left-hand edge and a second finger underneath the right-hand edge. And as a result, with these two fingers, we would apply an upward force and we would support the object. However, if we try to imagine what happens as we move the second of these two fingers to the left, when the two fingers are placed to the left over here, the object will simply fall. It will rotate around the rightmost of those two fingers, but it will nonetheless fall. Try this with your pen. Simply place the pen against your two fingers that try to support it from underneath, where your two fingers are both to one side of the center of mass. As you release your pen, it falls to the ground. Clearly, this is not the way to hold the pen stationary. We cannot direct the force from both supports upward and expect the pen, nor the diving board, to avoid falling. Instead, imagine holding your pen once again and orienting your hand as follows. Here I've drawn an outline of your hand, making a slightly opened OK symbol, such that your thumb is at the location of the quote-unquote center support, and your index finger is applied to the leftmost support. You can see that by pressing down with the index finger and up with the thumb, you are now able to support the mass of the pen, and so we will be able to support the diving board so long as the leftmost support points downward and the quote center support applies its force upward. With the correct directions and locations of the two forces coming from the supports for the diving board, we now have a complete free body diagram and we're ready to analyze it. The first thing we recognize is that all of the forces are in the vertical direction. So for Cartesian dimensions, we will have a y equation, but we will not have an x equation. That y equation is as follows. With upward as the plus direction, F2 is the only force in the up direction, and so our equation is as shown here. Since there is no acceleration in the y direction, the forces in that direction sum to 0. We'll place a box around this equation and save it for later. The second equation in this problem will be the torque equation. We know that the torques sum to 0 as indicated by our observation that the object is not experiencing an angular acceleration. The interesting question is which axis is the object not accelerating around? And the answer is all of them. The object is not accelerating around the pivot of its left-hand edge. It is also not accelerating around a pivot in the center. It is also not accelerating around a pivot at the right-hand edge, and it's not even accelerating about an arbitrary point located over there. Because we have this degree of freedom in the problem, we can use it to our advantage. Just as in regular force problems, when we oriented the coordinate system with the acceleration to simplify the resulting equations, we can choose to locate the pivot around which the object is not rotating in a place that will give us an advantage. The advantage comes from the fact that each torque is a force times radius. If we were to place the pivot at the center, the 20g would not appear in our torque equation. However, since 20g is a known quantity, leaving a known quantity out of an equation is not an advantage. This means that there are two advantageous positions at which we could consider the pivot point. The first one would be to place the pivot point at the left, such that F1 would appear in none of our equations, and the second one would be to place the pivot point at F2 so that the force F2 would not appear in any of our equations. I think I'm going to leave F2 out of our torque equation, leaving the pivot point exactly as indicated. We'll select clockwise as the plus direction. It doesn't matter because there isn't actually an angular acceleration, and this will allow us to formulate the clockwise equation. What we need to do is identify those forces that lead to torques in the clockwise direction. Imagine, if you will, a pin sticking through that pivot, and whether each force in question is attempting to rotate the entire figure either clockwise or counterclockwise around that pin. We recognize that there are two forces attempting to rotate clockwise around the pin. The first one is the gravity force acting on the diving board itself, and that is of an amount 20g. 20g represents a force. It is not a torque. Torque is force times radius. Radius is the distance between where the force is applied and where the pivot is located. Going back to our original figure, we see that the distance from the left-hand edge to force 2 is 1 meter. Since the diving board has an overall length of 5 meters, the distance from the left-hand edge to the gravity force is 2.5 meters, meaning that the distance from the gravity force to our chosen pivot is 1.5 meters. This completes the torque due to the gravity acting on the diving board itself. The other force that creates a torque in the plus direction is the 80g from our weight. 80g represents the amount of force, but it is not a torque. To get a torque, we need to multiply by radius, where radius means the distance between where the force is applied and the location of the pivot itself. Since the pivot is 1 meter from the left, and the diving board is overall 5 meter long, the radius associated with the 80g force will be 4 meters. This completes our analysis of all forces that lead to torques in the clockwise direction. Clearly, we have one more force, and this one leads to a torque in the counterclockwise or negative direction, and that will be F1. F1 is a force, and it is applied a distance of 1 meter away from the pivot, and so this quantity represents the torque due to F1. Because there is no angular acceleration, the sum of the torques must be 0. This equation then leads very simply to the value for F1. F1 is equal to 3,430 newtons. This is significantly higher than the sum of the weights of the board and the person. And the reason is, since the force F1 is applied with the smallest radius, it is at a mechanical disadvantage, meaning that you need much more force from that one to balance the torques from the other two. Now that we have a numerical value for the force F1, we can use that inside the equation in the box to get the numerical result for the force F2. F2 is equal to 4,410 newtons.